Hello dear students, today we shall learn Norton's theorem. In the previous sessions we learned about Thevenin's theorem and we know now how to simplify a complicated network consisting of several impedances, linear impedances and generators, and how it can be Thevenized to make it a very simple circuit, and how you can calculate the current flowing through the load resistance. So here we know that when you have a network of generators and impedances, it can be replaced by a single source ETH, and the whole impedances can be replaced by a single impedance ZTH, both of them in series. Okay, so this complicated network ending at the two terminals A and B can be replaced by a very simple circuit, again ending at the terminals A and B. Okay, so this much part was made equivalent to this much part. Then it was quite easy to find out the current flowing through the load resistance ZL. So this we have understood, and with problems we understood how you calculate the load resistance. And today we are going to understand about Norton's theorem, another theorem which is very similar to Thevenin's theorem, but there are some quite significant differences. Okay, so in that is also another theorem where you are able to simplify a complicated network. Okay, so we shall study that. So this is the Norton's theorem, and where you have as you had in the earlier case, a complex network consisting of generators and impedances. Then and it is ending up at the two terminals A and B. Okay, then you have the impedance connected, the load impedance. Now when we want to find out the current flowing through the load impedance, it may be quite complicated as the circuit is a bit complicated. Then what you can see we can do according to Norton's theorem is you can again simplify that. So how you simplify in the case of a Norton's theorem is that the whole network can be simplified, or it can be made equivalent to a current generator. The current generator, the current it produces is IN. Okay, then a parallel impedance to the current generator. So the whole part of this much, all the networks which is left to this line, that is this complex part, can be made equal to a current source in parallel to the impedance. So this is just in the case of Thevenin's, you know that it was instead of IN you had a voltage source, and instead of ZN you had impedance which was in series with the IN, not in parallel. Okay, but here in the case of Norton's theorem, when you simplify this complicated network, it becomes equivalent to a very simple circuit where you have all the generators are replaced by a current source which we denote here as IN, and all the impedance as replaced by a single voltage, a single impedance ZN, which is kept in parallel to the IN. Okay, so so this is the simplified form of this circuit. Then you can easily find, using this simplified circuit, you can easily find what is the current flowing through this load. Okay, so now we can actually make a definition for this Norton theorem. That is, one more thing is that when you make it as an equivalent current source, you must know how this current source has to be found out and what is this actual impedance. When you replace this whole thing by a current source, we should be knowing what is this, how you can calculate this IN, right? Similarly, how you can calculate this ZN. So that also you can understand. That is, any two-terminal network consisting of linear impedances and generators, that is such a circuit, it can be replaced by a current generator, this one, in parallel with an impedance, this one. Okay, now how you can find out this current? Okay, this current is equal to that obtained through a short circuit across the two terminals. That is, how you can get this IN is that from in this circuit, when you actually remove the ZL and short circuit the A and B, that is, you make both of them join together, or you make both of them connect together. That is a short circuit path, which means you remove the impedance and then you connect both of them A and B. Okay, so this is against the open circuit thing which you have seen in the Thevenin's theorem. So in the Norton's theorem, instead of keeping the AB open circuit, we make A and B short circuit. Okay, so remove ZL, then you make A and B short circuited. Then during that time when AB is short circuited, whatever current is flowing through this AB path, then that is actually, that current is what you replace by replace here with. So we can say that the current source IN is equal to that obtained through a short circuit across the two terminals. So when AB is short circuited, whatever current is flowing through that AB, that is actually the IN. Okay. Now what is the impedance ZN? And the impedance is that viewed across the two terminals when all the generators are replaced by their internal impedances. So what is ZN? ZN is the impedance. Again, at the two terminals, when you look the circuit from these two terminals towards this, what is the equivalent resistance? Okay, but when you remove all the generators by their impedances, so you may be having several generators, voltage or current generators. If you remove all of them and replace it with their impedance, and then you look from A, B towards this complicated circuit, what is the total equivalent impedance? That impedance is actually ZN. So now you understood that Zn is same as that as the Zth. So in both the theorem, Norton's as well as Thevenin's theorem, the resistance which you put along with the source in the simplified circuit are both the same, or they are found in the same way. So that means both Zn and Zth would be the same. So I will read out once more, then you will understand it clearly. So any two-terminal network consisting of linear impedances and generators may be replaced by a current generator in parallel with an impedance. The current is equal to that obtained through a short circuit across the two terminals, and the impedance is that viewed across the two terminals when all the generators are replaced by their internal impedances. So I hope that now this theorem is clear. Now we shall just look more into the detail with using an example. So here shown is a network which is not very complicated, but then you have a network of resistances and there is a voltage source here. You have the load resistance here. Now this circuit, this network can be replaced by a Norton equivalent circuit. How is done? How that is actually done? You know that first we have to find a short circuit current. So short circuit current is that current. You know that when AB is short circuited, whatever current is flowing through that is actually the short circuit current. So for that the load is removed. You can see here load is removed and the current will be flowing through AB, easily flowing through AB because of the lower resistance, no resistance there. And this current whatever is flowing through AB is actually IS, short circuit current. And it is this current with which you are replacing or which you are actually keeping in the equivalent circuit. Finally, this current is actually will be replaced in the equivalent circuit, or in the equivalent circuit the current generator is there and that current generator will be this one. Now the next step is to find the equivalent resistance. Here it is termed as R internal, but then you can just see. So for that what you have to do, as in the case of the Thevenin's theorem, you just look from the terminals A and B. There is no load here and it is actually the resistance felt at these terminals A and B. So from the terminals A and B, if you look towards this network, what is the equivalent impedance? And that is actually the RINT, which is denoted here. Now it is we have found out both the short circuit current and we have found out the Norton's equivalent resistance. Now what we have to do, the whole network can be replaced by this ISC in parallel with this impedance RANT, which is I have used this name as is shown in the figure. Okay, so now with this equivalent circuit, with the whole circuit replaced by this equivalent circuit, you can easily find out what is the current flowing through the load IL. Okay, so this is the actual interpretation, or we were actually explaining more in detail about the Norton's theorem. Okay. So now the thing is that you know that a complex network can be replaced by either by a Thevenin's equivalent circuit. So that is, this is the Thevenin's equivalent circuit. Okay, where you have the all impedances and generators, all the things were replaced by ETH, and in series to that the ZTH, that is the Thevenin's equivalent resistance impedance. Okay, okay. Now we have studied now the Norton's equivalent circuit. So as per that, we know that the whole circuit can be replaced by a current source IN in parallel with the impedance, Norton's equivalent impedance, which is same as the Thevenin's equivalent impedance. Okay, here it is termed as Zn. Okay, now we have already discussed and derived the current flowing from in a Thevenin equivalent circuit, the current flowing through the load resistance IL from this, which we have already derived in the previous session, that IL is actually equal to ETH divided by ZTH plus ZL. That you can simply find out from the circuit what will be the current IL. IL is the current. So when how will you find out the current flowing through ZL? This current is actually flowing through the network. So you can say that is the voltage divided by the total resistance will give you the current. So here voltage is ETH divided by ZTH plus ZL. Okay. So now coming to the Norton's equivalent circuit, we will find out what is the IL. Okay. Now you see, but then here it's not as simple as this. You cannot write like this because you know that the current impedance Zn is parallel to ZL. So when the current flows through the generator produces the current IN. So this current reaching the node here will split here and towards here. So obviously the way of finding the current is not this equation. Okay, and you have already learned the current division rule, that if you know the main current flowing from the source, you know here the main current which is being split as 2. This IN is the main current which is getting split into 2. So if you want to find the current passing through one of the branch, and that which is the current which is actually originating from the main current. Okay, if that is the case, I can find out IL as equal to first the main current IN. Okay, we have to find the current flowing through ZL, right? So first we have to write here the main current IN, then the current opposite to the, sorry, the impedance opposite to this branch. So this is the branch through which you are finding the current. So opposite to that branch is actually Zn. Okay, so that the impedance of the opposite branch divided by then impedance of the opposite branch plus impedance of the same branch, that is ZL. So actually from this circuit the IL can be written as the main current IN multiplied by impedance of the opposite branch Zn divided by impedance of the opposite branch plus impedance of the on branch. Okay. So now but now we know that from the calculation of this equivalent resistance, you know, or you already know that ZTH and Zn are the same because they are calculated in the same way. That is the equivalent impedance which is felt at the terminals A and B when all the sources are replaced by their internal impedances. So it is same in both Norton's case as well as in Thevenin's case. So now I can replace this Zn with the I can replace this Zn, which ZTH. So I can write it as In into ZTH divided by ZTH plus ZL. Okay. Then one more thing. You know that this part here you have ETH and then in series with ZTH. So what will be actually this In? In should obviously be the voltage, Thevenin's voltage divided by the resistance, whatever is that, that will be the actual source here, right? So In is actually the current flowing from the generator, and I can say this current In will be obviously equal to this ETH divided by this ZTH. So I can write this In as equal to ETH divided by uh, the ZTH. Okay. From the circuit, it is obvious that this current which is coming from the generator should be equal to the ETH divided by ZTH. So then I can replace this In also. Okay. So if I replace, then I can write ETH divided by ZTH. So replaced In. Then ZTH plus ZL. Okay, so now you see this other is one more ZTH here. This is ZTH will get cancelled. So cancelled, then I can get ETH divided by ZTH plus ZL. Now you see both the current are the same. So that is the IL and I here. IL calculated using the Thevenin equivalent circuit and IL calculated using the Norton equivalent circuit are the same, and it should be the same, right? Because you are simplifying a same network. A same network was replaced in two ways. One I made it equal to the Thevenin equivalent circuit. Then the next case I made it equivalent to the Norton's equivalent circuit. In either way, finally the current flowing through the load resistance should be the same. These two theorems are two ways of actually representing a complicated network. But here instead you had a voltage source, but here instead of the voltage source you had a current source, and that impedance is also put in a different way. That is all. And many times you can use both the circuits to simplify the complicated network which is given to you. But then when you normally deal with current sources, so for example when you are dealing with transistors and all, we consider them as current sources. So in that case we normally in a circuit with the transistors we simplify those such circuits as a Norton equivalent circuit and then simplify it. Okay, so what we discussed in the current session was what is actually Norton's theorem. So Norton's theorem, we understood how you can represent a complicated circuit into a Norton's equivalent circuit, and where the whole thing can be replaced by a current source, and which is in parallel with the impedance, Norton's equivalent impedance. And this current source is actually the current flowing at the terminals A and B, at the two terminals when they are short circuited. And the impedance is actually the one which is experienced at the terminals AB when all the generators are replaced by their impedances. And you understood that both are same, actually Thevenizing a circuit and finally Nortonizing a circuit, both of them finally come at the same conclusion of getting, or they actually help us to find the same thing only. Okay, but these are the two ways of representing a complicated circuit, and they help us to simplify or find out the current passing through the load. Okay, I hope you understood. If you have any confusion or doubts, you can please put it in the comment box. Thank you very much.